Hello everyone. In this module, we are going to continue with the mass spectrometric topic, and under that, today we are going to study about isotopic abundance or isotopic cluster followed by various fragmentation patterns in mass spectrometry. As soon as we say isotope, it is the one which has got same molecular formula but difference in the molecular weight or atomic weight of the sample. So depending on the isotopic abundance, there will be different mass ions in the mass spectrum of a particular compound. Say for example, the carbon, it exists in three different isotopes. The first one is C12, second is C13, and one more is C14. We will not take C14 into consideration now because it is almost negligible. Carbon C12, it has got this is Na is natural abundance. It has got 98.9 abundance. This is a very high abundance, the natural isotope. Almost all these elements given here are the natural isotopes, whereas C13, it has got the natural abundance of only 1.1%. Whereas hydrogen, it has got two isotopes, 1H, which is having the natural abundance of 99.989%, and 2H, that is deuterium, it exists only in 0.015% natural abundance. That means to say here, among 1H and 2H, 1H is most abundant, and among C12 and C13, C12 is most abundant. Coming to nitrogen, it has got N14 and N15. N14 has got 99.635% natural abundance, whereas N15 has got 0.365%, meaning that N14 is the highest abundant isotope of nitrogen. Coming to oxygen, it has got three isotopes, O16, O17 and O18. All are oxygen. They all differ by only one mass unit in the case of oxygen. O16 is 99.759%, O17 is 0.037%, O18 is 0.204%, and cumulative of all this will be 100%. This will become M plus O16. O16 plus 1 is O17, that's why it becomes M plus plus 1. This is O18, O16 plus 2 is O18, that is, it is becoming M plus plus 2 peak. So oxygen has got three different peaks around M plus plus 1 and M plus plus 2. Even sulfur has also got three different isotopes. Sulfur 32, it exists in 95.018%, S33 0.75%, S34 is 4.215%, in which S32 will be M plus, S33 will be M plus plus 1, S34 will be M plus plus 2. The highest abundant is S32 followed by S34, and the least abundant among sulfur isotopes is S33. Coming to chlorine, it has got two different isotopes, Cl35 and Cl37. Cl35 exists in 75.53%, whereas Cl37 exists in 24.463%. So this will be M plus and this will be M plus plus 2. Why it is M plus plus 2? Because there will be two mass units difference between Cl35 and Cl37. 35 and 37, two mass units. That's why we don't see M plus plus 1 peak in case of chlorine. Only we will see M plus and M plus plus 2. In case of bromine, we have got two isotopes, bromine 79 and bromine 81. So bromine 79 exists in 50.52%, whereas bromine 81 exists in 49.48%, and also the mass units difference between these two isotopes of bromine is 2, and hence we are going to observe M plus peak as well as M plus plus 2 peak, and no M plus plus 1 peak, both for chlorine as well as bromine. Here you can see that the difference or the ratio intensity will be 3:1, and it is almost 1:1. And whereas the last three elements, say fluorine, iodine and phosphorus, they are all monoisotopic, meaning that they have got only one isotope. There are no naturally occurring isotopes of fluorine other than F19, for iodine other than I127, for phosphorus other than P31. That means there is only one naturally occurring isotope of fluorine, iodine and phosphorus. Fluorine will be F19, iodine will be 127, phosphorus will be 31. This is about the natural isotopic abundance, or we can also call it as isotopic cluster. Among all these, the most characteristic features are with respect to chlorine and bromine, because its isotopes are very, very heavier, whereas the rest of the isotopes you can see it is just within 5% or within 4%, that is as that for sulfur 34, whereas for chlorine and bromine they have got very high percentage of the isotopes. One is 75, another one is 24, one is 50, another one is 49. So roughly 1:1. This is roughly 3:1. That's why these two takes a special place in the isotopic abundance with respect to mass spectrometry. So to conclude here, we know that ions containing different isotopes, they appear at different MZ value because they differ by different mass units. For an ion containing n carbon atoms, there is a probability of 1.1 into n% of these atoms will be C13. That means to say that, so in order to in order to calculate how many C13 are there in the given compound, it can be easily calculated by using the formula 1.1 into n%. Here n is number of carbon atoms and 1.1 will be the natural abundance of C13, and C12 we are disregarding that one. So this will give rise to an ion of mass 1 unit higher than the ion that contain only carbon 12 atom. So say for example, if you take 2-methyl pentane, so there will be an associated M++1 peak whose intensity is approximately 6.6% of that of the molecular ion. So you can see that this is the mass spectrum of 2-methyl pentane. Here 86 is the M+, and you can see that for M+, there are two peaks. One is M+, another one is M++1, and M++1 is roughly 6.6% higher than that of the molecular ion, the intensity. So how we know that it is 6.6%? We will calculate that. The formula is 1.1 into n%. 1.1 is the natural abundance of C13, n is number of carbon atoms. So in the case of 2-methyl pentane, we have got 6 carbon atoms. How? Pentane is 5, methyl is 1. So 5 plus 1 is 6. Totally 6 carbon atoms. So n becomes 6. N into 1.1, 6 into 1.1, it becomes 6.6%. So this is how we can calculate the percentage of n++1 peak associated with the molecular ion. Next is, if there are more than one carbon atom in an ion, we know that any organic compound cannot contain only one carbon. Exceptional cases are there, of course. And if there are more than one carbon atom, then what is the probability of this atom being C13? That can be easily calculated by using the binomial expression A C12 plus B C13 whole raised to n. Here A is percentage of natural abundance of lighter isotope, B is the percentage of natural abundance of the heavier isotope, whereas n is the number of carbon atoms present in the ion. So in the case of carbon, it becomes C12 because this is the lighter isotope of carbon, and this becomes C13 being the heavier isotope of carbon. So A is percentage of natural abundance of lighter isotope, whereas B is percentage of natural abundance of the heavier isotope whole raised to n. N gives the number of carbon atoms present in the ion, and using this binomial expression, you can calculate that how many of the carbon atoms present in a compound are C13. As I said, among different elements present in the periodic table, halogen isotopes takes a special significance because of the presence of chlorine and bromine. We know that chlorine, it gives 3:1 peak, whereas bromine, it gives 1:1 peak, because both the isotopes of chlorine and both the isotopes of bromine, they have got very high percentage of isotope natural abundance. We know that chlorine, it has got two isotopes, Cl35 and Cl37, and their percentage is 75:25, that is in the ratio of 3:1. Whereas bromine also has got two isotopes, 79 and 81, and roughly 50.2 or 49.8, roughly 1:1 we say, and hence its intensity will be in the ratio of 1:1. That means to say, if at all there is a chloro in the compound, then you will see that two peaks will be appearing, and the two peaks will be of 3:1 ratio intensity, and this is the chlorine isotope pattern. Here you can see that one is of 75%, another one is of 24%. One is due to Cl35 and another one is due to Cl37. The same is case is the of bromine. Bromine has got two isotopes, 79 and 81. So 79 will be 50.8, whereas 81 will be around 49.2 something, and roughly I can say that it is 1:1 intensity. This is from 79 isotope of bromine, and this is 81 isotope of bromine. So this will be the bromine isotope pattern, whose intensity ratio will be approximately 1:1, and the chlorine intensity pattern or isotopic pattern will be 3:1. So as a result of that, these characteristic molecular clusters will appear at M plus, M plus plus 2, M plus plus 4, etc. In the sense that ions containing one chlorine atom exhibit relative intensity of lines 3:1 ratio, whereas ions containing one bromine atom, they display lines of roughly equal intensity and separated by 2 mass units. You can ask why 2 mass units, because 35, 37, 79, 81, the difference between them is 2, and hence we can say that it is M plus plus 2 peak are separated by 2 mass units. So now we have to go for some expression, we will see. So for each halogen isotope, the intensity ratio of molecular ion clusters may be calculated by the binomial expression, the same thing, A plus B whole to the power of n. Here A is the relative abundance of the isotope, that is A is lighter isotope, B is heavier isotope, where n is the number of atoms of these present in the ion. We can say that when n is equal to 2, here A plus B whole raised to 2. So n becomes 2, substitute in place of n 2, it becomes A plus B whole square. We know the expansion for this, A square plus 2AB plus B square. When n becomes 3, it becomes A plus B whole cube, whose expansion is A cube plus 3A square B plus 3AB square plus B cube. Like that, you can calculate for any number of atoms present in the molecule. Now, we will go for some solved exercise. If 2 chlorine atoms are present in a molecule, then how we have to calculate the intensity of the peaks present in that. So when 2 chlorine atoms are present, we can see peaks around M plus plus 2 and M plus plus 4. Here when 2 chlorine, that means N becomes 2 here, here N becomes 2, and A becomes 3, B becomes 1, N becomes 2. How A is 3, B is 1? Because the chlorine intensity ratio is 3:1. So 3 is for lighter isotope, 1 is for heavier isotope. So it becomes A plus B whole square. We know the expansion, A square plus 2AB plus B square. A is 3, it becomes 3 square. 2 into A is 3, B is 1, 2 into 3 into 1 plus B square, B is 1, 1 square. So here 3 square is 9. 3 times 2 is 6, 1 square is 1. So 9:6:1 is the line intensity ratio of chlorine atoms in case of compounds containing 2 chlorine atoms. Now we will move to the next solved example. What if 1 chlorine and 1 bromine is present in the molecule? In the earlier case, we saw if there are 2 chlorine atoms present in the same compound, but there may be a compound which has got 1 chloro and 1 bromo, then how to calculate the line intensity ratio for such a compound? Here in this case also we can see peaks for M plus plus 2 and M plus plus 4. So here there are 2 different atoms. When there are 2 different atoms, we cannot use only A plus B. We have to go for the next expression, C plus D. Here A plus B will be for chloro, C plus D will be for bromo. Here in this case, there is only 1 chlorine, there is only 1 bromine, so N becomes 1 here. So A plus B whole power N, it is nothing but A plus B, C plus D whole power N, so it becomes just C plus D. Now we have to multiply AC, AD, BC, BD. Multiplication, simple multiplication, so it becomes AC plus AD, BC plus BD. So AC will become M plus, AD become M plus plus 2, BC becomes M plus plus 2, BD becomes M plus plus 4. Now you might ask, why AC becomes M plus? It is because of the simple reason that in case of AC, A is lighter isotope, B is like heavier isotope. In case of C plus D, C is lighter isotope, D is heavier isotope. So AC. So first one is lighter. Here in this case, both are lighter isotopes, and hence it becomes M plus. In case of AD, one is lighter and one is heavier. Because of that, we get M plus plus 2P. In case of BC, one is heavier, one is lighter. That's why we get M plus plus 2P. Whereas in the case of BD, Both are heavier isotope, heavier. Both are heavier isotope. As a result of that, we are going to get M++4 peaks. So in this case, this is for chloro, this is for bromo. A will be 3, B is 1. In case of bromo, it is C and D. It is 1:1 ratio. So C becomes 1, D becomes 1. That's why here A is 3, B is 1, C is 1, D is 1. Now we have to substitute A, B, C, D in this expression. AC plus AD plus BC plus BD. So it is A into C. A is 3, C is 1. 3 into 1 plus AD. A is 3, D is 1. 3 into 1 plus BC. B is 1, C is 1. Next is BD. B is 1, D is 1. So what it happens? 3 into 1, 3. 3 into 1, 3. 1 into 1, 1. 1 into 1, 1. Now, outermost we have to keep it as such. The middle ones we have to add up. So 3 keep it as such, 1 keep it as such. Middle one you just add up, 3 plus 1 becomes 4. So it will become 3 plus 4 plus 1. You should not add up. So that is the peak intensity ratio. If there are 1 chloro and 1 bromo present here is 3:4:1. That will be the peak intensity ratio of a compound if there is only 1 chloro and 1 bromo in the compound. Next we will move to another solved example. What if a compound has got 2 chloro and 1 bromo? That is very, very important. Right? In this case, we are going to see M++2, M++4, M++6 peaks. Right? And so there are 2 chloro. 2 chloro is A plus B. Bromo will be always C plus D. So chloro A plus D. A plus B. There are 2 chloro. So whole raised to N. N becomes 2. So this becomes A plus B whole square into C plus D. There is only 1 bromo. So C plus D whole power N. It becomes just C plus D. Now we have to expand this A plus B whole square. It is A square plus 2AB plus B square into C plus D. This is not the final expression. So we have to combine this equation. What it becomes? A square C plus A square D. 2ABC plus 2ABD. B square C plus B square D. That is what is the final expression we are going to get if there are 2 chloro and 1 bromo. In this case, A square C is M plus, A square D is M plus 2, this is M plus 2, this is M plus 4, this is M plus 4, and this is M plus 6. We know why? Because A, B, this is light, this is heavier, this is light, this is heavier. AC, both light isotope, and then it becomes M plus. In case of AD, one is heavier, one is, this is lighter, this is heavier, therefore it is M plus 2. In ABC, also, one is, 2 are heavy, one is light. That's why it becomes M plus 2. In ABD, what happens? One is light, 2 are heavier. That's why it becomes M plus 4. So you have to give the higher mass unit. Next is B square C, B square. So there are 2 heavier isotopes, 1 light isotope. That's why we have to give for the higher M plus 4. The last one is B square D. Here B and D both are heavier and there are 2 B's. That means it should get the highest value, that is M plus 6. And in this case, A becomes 3, B becomes 1. C becomes 1, D becomes 1. So substitute A is equal to 3, B is equal to 1, C is equal to 1, D is equal to 1. In this final expression, we are going to get this. So A square C, A is 3 square into 1. Next A square D, 3 square into 1. 2 ABC, 2 into 3 into 1 into 1, A 2 ABD, 2 into 3 into 1 into 1, B square C, 1 square 1, B square D, 1 square into 1. So when you solve this, you are going to get 9, 3 square is 9, 9 into 1 is 9, 3 square into 1, 9 into 1, 2 into 3, 6, 6 into 1, 1, 6 into 1, 1, 6, 2 into 3, 6, 6 into 1, 1, 6 into 1, 1, 6, 1 square is 1, 1 into 1, 1, 1 square is 1, 1 into 1 is 1. So now what we have to do? We have to leave the outer ones as such. So 9 and 1, you keep it as such. Middle one you should add. So middle one, how we have to add? These 2 combines 1 and these 2 combines 1. 9 plus 6 is 15, 6 plus 1 is 7. So it will be 9 plus 15 plus 7 plus 1. We are not supposed to add up. So its intensity will be 9 is to 15 is to 7 is to 1. We are going to get 4 peaks of these masses. M plus 2, M plus 4, M plus 6. So 9 is to 15 is to 17 is to 1 is the peak intensity ratio for the compound if it contains 2 chloro and 1 bromo. Similarly, you can calculate for any number of chloro and bromo in a compound. You can say 2 bromo and 1 chloro. If there are 2 bromo, what you have to do? A plus B into C plus D whole square. Always A plus B for chloro, C plus D for bromo. That you have to remember. Then N, it depends on number of chloro and bromo present in the compound. So based on this, in general, we can have one thing here. So this table clearly gives the number of peak intensity ratio. If there is there is only 1 chloro in the compound, you are going to get 2 peaks, and that will be whose intensity will be 3:1. If there are 2 chloro, then you are going to get 3 peaks of the intensity 9:6:1. Sir, how did we get this? It is very simple. You have to do A plus B whole square because there are 2 chloro atoms. So N is equals to 2. Substitute in A square plus 2AB plus B square. In case if there is only 1 bromo, it is going to give 2 peaks of roughly 1:1 intensity. If there are 2 bromo, it is going to give 3 peaks of 1:2:1 intensity, right? And what if there is 1 bromo and 1 chloro? Then it is going to see 1 bromo and 1 chloro is going to give 3 peaks in the ratio of 3:4:1. What if there is 1 bromo and 2 chloro? Then you are going to get 4 peaks of 9:15:17:1. This is what we solved just now. And if there are 2 bromo and 1 chloro, then you are going to get 4 peaks of intensity ratio 2:7:8:1. What if there are 2 bromo and 2 chloro? Then you are going to get 5 peaks of the ratio 9:24:22:8:1. So this table, a generalized table, it will give the number of peaks as well as the ratio of intensity of the peaks obtained in case of just permutation and combination of bromo and chloro. Only chloro, only bromo can also be calculated. The combination of chloro and bromo, the combination of chloro and bromo in different terms can also be calculated to arrive at this number of peaks and this relative intensity ratio. So this is the characteristic feature of chloro and bromo. This we don't see in any other element because chloro and bromo, its severe isotope percentage, natural percentage abundance is very high when compared to rest of the elements present in the periodic table. That's why we give a special significance for chloro and bromo in the mass spectrum. Coming to exercise based on this chloro and bromo. Question number 1. Calculate the relative abundance of the halogen isotope peaks in the molecular ion of 1,3-dichloropropane. Ignore any contribution from C13. You have to read the question carefully. He is asking us to calculate the relative abundance of the halogen isotope peaks in the molecular ion of this compound 1,3-dichloropropane. So propane is this 3 carbon atoms, and at 1 and 3rd position, 1, 2, 3, you have to substitute chloro each. So this compound contains 2 chloro, right? When there are 2 chloro, we know that we are going to get 3 peaks, M plus plus 2 and M plus 4. So you have to put the equation A plus B whole power n. Here in this case, because there is only 1 chloro, we know that the intensity ratio for chloro is 3:1. So A becomes 3, B becomes 1, and N becomes 2. Why? There are 2 chloro atoms, chlorine atoms. That's why N is equal to 2. Therefore, it becomes A plus B whole square. We know the expansion A square plus 2AB plus B square. A is 3 square plus 2 into 3 into 1 plus 1 square. So 3 square is 9, 2 into 3 is 6, 1 square is 1. So this is the line intensity ratio for chlorine atom for 1,3-dichloropropane. Now we will move for the next problem. Calculate the isotope pattern, mass and relative intensities in the molecular ion region for a compound having 3 bromine atoms, right? Say it is 1,3,5-tribromobenzene and another compound with 2 bromine and 1 chlorine atom, say 1-chloro-3,5-dibromobenzene respectively. So this problem has got 2 problems inside that. First one is 3 bromine atoms. So it can be 1,3-tribromobenzene, 1,3,5-tribromobenzene. So we'll take up the first problem. What if there are 3 bromine atoms? In this case, N becomes 3. We know that A plus B whole to the power of 3, A plus B whole cube. The expansion is simple, A square, A cube plus 3a square b plus 3ab square plus b cube. Here a is 1, b is 1 because they have given only bromine. Bromine, its intensity ratio is 1:1. So both a and b becomes 1 here. So substitute a and b value in this final expression. It becomes 1 cube plus 3 into 1 square 1 plus 3 1 1 3 into 1 into 1 square plus 1 cube. So it becomes 1 cube is 1, 3 into 1 square into 1 is 3, 3 into 1 into 1 square is 3, 1 cube is 1. So it will be 1:3:3:1. So you are going to get 4 peaks whose intensity will be 1:3:1. That's why we are going to see m plus 2, m plus 4 and m plus p plus 6 peaks are seen in the mass spectrum of 135 tribromobenzene or any compound having 3 bromine atoms. Now we will move for the second problem. Second problem, he says that the compound contains 2 bromo and 1 chlorine atom. So it is 1 chloro, 3,5 dibromobenzene. So there are 2 bromine. So we can say a plus b whole square into c plus d, 2 and 1. So a square plus 2ab plus b square into c plus d. So it becomes this, and these are the peaks we are going to get. Here a, b will be 1:1, c, d will be 3:1. And when you substitute this in the final expression, you are going to get 3:7:5:1. So the peak intensity ratio, and the peaks are seen at m plus 2, m plus 4 and m plus 6. So these are the different problems in order to calculate the line intensity ratio for any compound containing any number of chlorine and bromine. So you must remember clearly that this is applicable only for compounds containing chloro and bromo, no other halogen, no other element, in particular with the mass spectrometry. So this is all about the natural abundance of isotopes, or we can say that isotopic abundance or isotopic clusters, right? Next item that we have got to study in the mass spectrometry is fragmentation patterns. We know that whenever you have a molecule and it is hit with very high energetic fast moving electrons, then the molecule will lose an electron to form M plus radical, that is called molecular ion. Because the energy of the electrons is so high that you cannot stop at only the molecular ion stage, the additional energy present in the electrons, it will bombard the molecular ion, and the molecular ion will undergo rupture to form different daughter ions. They are also called as fragment ions. How the fragment ions are formed and what is the process called, that is what is studied under fragmentation patterns. So how we can define fragmentation pattern? It is the breakup process of the molecular ion into smaller ions. The smaller ions are called fragment ions or daughter ions. So what is the significance of fragmentation? In what way it is helpful for us? This fragmentation is highly helpful for us in the structural elucidation of organic compounds because it takes place in a systematic way. Step by step way the fragmentation takes place. So the relative abundance of the fragment ion form, it depends on the stability of the ion and also on the stability of the radical loss. So we know that whenever a molecular ion is undergoing bombardment with the fast moving electrons or highly energetic electrons, you can say that you will get both a positive ion as well as a radical. So your relative abundance of the fragment ion, it depends both on the stability of the ion as well as the radical. So in what way we can judge the stability of the ion? It can be judged based on the stabilization of the charge, which depends upon resonance, inductive effect, polarizability effect and other parameters, and these parameters determine the stability of the ion form. If the stability of the ion is greater, then its relative abundance will be very, very high. That means you are going to get very strong peaks in the mass spectrum. You say, for example, if the ion or the cation or the daughter ion form has got very, very less stability, then its peak intensity will be very, very less in the mass spectrum. So the relative abundance of the daughter ion form mainly depends on the stability of the cation form. So higher the stability, more will be the intensity and vice versa. We will see different modes of cleavage now. Fragmentation, it can also be called by the name cleavage. In cleavage, we have got the first one, simple cleavage. Another simple cleavage, we have got to study about homolytic cleavage. Homo means same, lytic means breakdown. Same, breakdown, cleavage. Under that we have got three categories: mode 1, mode 2 and mode 3. Here is the first case, that is mode 1. It is also called alpha cleavage. It is very simple. So whatever is alpha to the functional group, that bond will be cleaved off. That is called alpha cleavage. So alpha cleavage is seen in compounds containing a heteroatom which is attached to the carbon atom by a single bond. Here, this is the example. X is the heteroatom. X can be either hydroxyl or NH2. They are primary amine. So O is heteroatom, N is heteroatom. Think that in place of X, OH is attached. So mode 1 cleavage or alpha cleavage is seen in those compounds in which this heteroatom should be attached to carbon through a single bond. In such case, you will see homolytic cleavage. So this becomes the functional group and this bond becomes alpha, or this bond becomes alpha. Both the bonds can be subjected, only one at a time. Here for reference sake, we have taken this bond as alpha bond. So what happens? This is the functional group and this is alpha bond. So we can say that this is homolytic cleavage. Homo means same, lysis. That means this bond will be cleaved equally. So one bond means there will be two electrons. Each electron is called as radical. Here one electron is given on this R, another electron is given for this bond. So this compound, whenever it is hit by the molecule, whenever it is hit by the highly energetic electrons, it loses an electron because these heteroatoms will have a lone pair. So among the lone pair, one radical is lost and remaining radical is present. This radical is also giving here one electron. So it is one electron reaction. That's why we have written half arrows, one electron to this and one electron to this. As a result of that, a new sigma bond is formed here. The new sigma bond is formed adjacently. So this is called as homolytic cleavage. As a result of that, you are going to get R radical plus C double bond X H R dash plus the plus charge will be retained on the X, whereas the radical will be given for the bond formation, and this is the new bond form. So here removal of one electron from the heteroatom leads to the formation of a molecular ion. A new bond is formed with the adjacent atom through the donation of the unpaired electron and the transfer of electron from the adjacent bond. So this is the adjacent bond. It is also called alpha bond. Now we will take up a particular example. Instead of X, I am taking OH here. So you have a compound. Maybe this is primary alcohol or secondary alcohol. So what happens in this oxygen? There is a lone pair of electron. Among the lone pairs, whenever I hit this molecule with the fast energetic electrons or highly energetic electrons, it loses one electron, so it becomes a molecular ion. In molecular ion, there is also called radical cation. So this is alpha cleavage. This is the functional group. Either this can be alpha bond or this can be alpha bond. For convenience sake, I have taken this one. So this is homolysis. That means one electron will be given to R, another electron will be given to this bond. This electron is also giving to this bond formation. So it becomes R radical plus CH double bond OH R dash, and on oxygen you will retain the positive charge, and this is called alpha cleavage or mode 1 cleavage under homolytic cleavage. So this is an ether. In this case, ether also we can see that alpha cleavage will be taking place. Here oxygen is the heteroatom. So you hit this ether with very highly energetic electrons. It loses a radical to form radical cation or molecular ion. Now the alpha bond should be cleared. So this becomes the functional group. This is the alpha bond. So one electron is going here, another electron is coming here, and this electron is also going here. It results in the formation of a new bond here. So this is the new bond, and the positive charge is retained by the heteroatom and our radical is formed. This is how mode 1 cleavage or alpha cleavage will be taking place in the compounds. What is mode 2 cleavage? Mode 1 and mode 2 are more or less different, whereas in the mode 1 we see that heteroatom is connected to carbon by a single bond, whereas in mode 2 it is also alpha cleavage, no doubt, but here heteroatom is connected to carbon by a double bond. So compounds containing a heteroatom which is attached to carbon atom by a double bond. So in such cases or in such compounds you will see mode 2 cleavage. Here alpha cleavage is the preferential fragmentation mode, and this mode 2 cleavage is shown by different classes of organic compounds having aldehydic, ketonic, acidic, ester or amide functional group, but this mode 2 cleavage is not seen in C double bond N or C double bond S groups. So here heteroatom is connected to carbon by double bond. So this type of compound show mode 2 cleavage. What happens here? Oxygen will have a lone pair. You hit this with very highly energetic electrons. So one of the electrons is lost, and this results in the formation of radical cation. Now do the alpha cleavage. This becomes the functional group. Either this can be alpha bond or this can be alpha bond. Here I have taken this example. So here one bond will be donated here. One bond will be donated to R1. Here there is one more electron. This will be donated here. So C double bond O becomes C triple bond O, and the positive charge is retained by the heteroatom oxygen. This is the case of mode 2 cleavage. This mode 2 cleavage is shown by compounds in which the heteroatom is connected to carbon by means of a double bond, whereas mode 1 is heteroatom connected to carbon by a single bond. That is the major difference between mode 1 cleavage and mode 2 cleavage. The next one is mode 3. It is called beta cleavage. The name itself is telling we have to cleave the beta bond. From where the beta bond, we will see. The cleavage of bond, that is beta, with respect to the charge or radical, that is called beta cleavage. Take an example. Here Z, it can be anything. On this Z, we have got radical and charge. From this radical and charge, we have to start counting the beta. So this is radical or charge containing element. This is alpha bond and this is beta bond. So here the beta bond should be cleaved. So what happens? These electrons will get transferred to here. So R becomes R plus and CZ becomes C double bond Z, and the radical is retained by this Z. So this is called beta cleavage. So to understand this more clearly, we will go for this example. This is N-butyl bromide. Here on this bromine, there is charge as well as the radical. So from this, we have to count the beta bond. So this is the charge center, this is alpha bond, and this is beta bond. So this beta bond should be cleaved now. So what happens? The electrons in the beta bond, it gets transferred here, and it becomes propyl cation CH3, CH2, CH2 plus. Along with that, CH2 double bond Br, the radical, that is radical charge, radical will be retained by the bromine. So this propyl cation, it undergoes rearrangement to obtain a very stable cation. So instead of CH3, CH2, CH2 plus, there will be a small rearrangement of hydrogen. This hydrogen moves here and it becomes CH3, CH, CH3, and on the middle carbon there will be positive charge. So this is a small rearrangement that is taking place in the propyl cation, and this is called beta cleavage. So in one nutshell, if you want to show both alpha and beta cleavage, we will consider the case of this compound. Here, this is bromine. So this is the heteroatom. We will first consider the alpha cleavage. So in the case of alpha cleavage, the alpha bond should be cleaved off. It is homolytic. One radical will be going here, and another radical will be going here, and it becomes benzene ring CH2 CH2 plus bromine radical. So whose MZ will be 105 and 50% will be the intensity ratio or intensity of this peak. And in case of beta cleavage, what does the beta cleavage says? So wherever is the charge or the radical, and from there you have to count the beta bond. So here is the charge, this is alpha bond and this is beta bond, and this beta bond should get cleaved off here. So the electrons present here will be moving towards this, and it becomes C6H5CH2 plus, and this is benzyl cation, and its intensity will be 100%. That means it will be having very, very good intensity in the mass spectrum. Why? Because this results in the formation of a rearrangement that we are going to see in the next slide, and it becomes a tropylium cation. In the tropylium cation, there will be resonance as well as the charge stabilization. As a result of that, there will be very, very high percentage of this, say 100%, and its intensity also will be the very, very high in the mass spectrum. Along with that, we are going to get CH2 double bond Br, and Br will be retaining the radical here. So in a nutshell, we have seen both alpha cleavage and beta cleavage in a simple compound. This is about the different types of cleavages under homolytic cleavage. Now we will be going for the rearrangement reactions accompanied by transfer of electrons. This is what we have to study now. Under that, there are two categories. The first one is hydrogen transfer reaction. This hydrogen transfer, the name itself is telling the hydrogen will be transferred from one place to another place or from one atom to another atom. As a result of that, this is considered as the simplest rearrangement that is taking place in the mass spectrometry. Usually, hydrogen atom is transferred from one atom to another atom over a pi framework. So, if there is any pi bond in the molecule, over that pi bond, the hydrogen will be transferred from one place to another place or from one atom to another atom during fragmentation. The best and the simple example is the formation of propylium cation, as I said a short while ago. So, this is propylium ion. It is formed by the benzyl derivative or benzyl cation by the rupture and cleavage of CH bond. So here this is benzyl cation whose MZ is 91 and this is highly unstable. As a result of that, the CH rupture will be taking place and the rearrangement taking place. The CH2 which is out of the ring, as a result of the rupture and cleavage, the C it becomes one of the components of the ring. So instead of 6-membered ring, as one more carbon is adding, we are going to get 7-membered ring, and this is charge stabilized. And here in this case, the electrons will be continuously revolving around this ring, and this 7-membered ring with a positive charge is called as propylium ion, or it can also be called as propylium cation, and its MZ is also 91, and its percentage or intensity percentage will be 100% in the mass spectrum because of the continuous resonance as well as the charge stabilization. How propylium ion is formed? So this, consider this as the toluene. In toluene, one hydrogen is lost and it becomes CH2. This is benzyl cation. For that one benzyl cation, what happens? There will be charge transfer taking place or hydrogen transfer taking place, and it becomes, instead of 6-membered, a 7-membered ring. And in this case, this one H will be lost and it forms a propylium cation. In short, it is termed or named as Tr plus. 3R plus referred to as propylium cation. So we can say in future propylium cation or Tr plus. And this is one of the simplest rearrangements that we are going to see in mass spectrometry, that is hydrogen transfer reaction or hydrogen transfer rearrangement. The second rearrangement that we have got to study is Macroparty rearrangement. Macroparty is the name of the scientist. He is the one, and in the honor of him, they have named it as Macroparty rearrangement. And in short, we can call it as MR. M is Macroparty, R is rearrangement. In this rearrangement, there will be migration of gamma hydrogen atom followed by the cleavage of a beta bond. This can be seen in this equation. Consider a molecule in which there is more than 3 carbon atoms attached to the functional group. That is the prerequisite for Macroparty rearrangement. So consider any functional group. To that, there should be a minimum of C3. That means 3 carbon atoms should be attached to the functional group. If 3 carbon atoms are not there, then no Macroparty rearrangement can be seen. So consider a ketone here. Ketone general formula is RCO, R dash. Here this becomes R. This R has got 3 carbon atoms, and among the 3 carbon atoms, there should be a gamma hydrogen. So this is functional group. This is alpha carbon, beta carbon, gamma carbon. Gamma carbon has got a hydrogen, and this hydrogen is called as gamma hydrogen, shown in red color. That gamma hydrogen will be migrating to the functional group. As a result of that, beta bond will be cleaved off or ruptured. This is called Macroparty rearrangement. So what happens here? They imagine a ketone. The oxygen is the heteroatom. It will be having a lone pair of electrons. So once you bombard with very highly energetic electrons, say 70 electron volt, one of the electrons will be lost from this oxygen, and it results in the formation of a molecular ion. That will be the first step. It is not shown here because the first step that is taking place in mass spectrometer is the formation of molecular ion. So this is the molecular ion. Now the gamma hydrogen, it is moving from this gamma carbon to the oxygen. As a result of that, this double bond is shifted here. beta bond gets shifted here. So you are going to get a cyclic 6-member transition state. In this transition state, the pi bond will be moving around the periphery of this 6-member cycle. This is a transition state, meaning that it is highly unstable. So what happens? This O becomes OH because this H is migrating completely along with this electron to the oxygen. This C double bond O becomes single bond O, but CC single bond becomes CC double bond here. So this is called Macroparty rearranged ion, or in short it is called as MR ion. Along with the MR ion, you are going to get a neutral molecule, say usually alkene in many cases. So in the Macroparty rearrangement, the products will be, one is Macroparty rearranged ion, another one is the neutral molecule, that is alkene. Usually this Macroparty rearrangement is seen in organic compounds having the functional groups like alcohol, amine, aldehyde, ketone, unsaturation, substituted aromatic, carboxylic acid, even amides. We can see easily Macroparty rearrangement. So if Macroparty rearrangement is taking place in a molecule, then you will usually see the molecular ion with an even mass in its mass spectrum. Usually this MR ion will always be appearing at even M by Z. We will see whenever we take up the different examples. So this is the first case. This is an alkene, 1, 2, 3, 4, 5. So this is 1 pentene. In this case, we have to always check whether there are 3 carbon atoms attached to the functional groups. These are the examples for Macroparty rearrangement of different classes of organic compounds. So this is the functional group alkene. Here there are 3 carbons, 1, 2, 3. So this is the functional group. This is alpha, this is beta, this is gamma. So what is Macroparty rearrangement? Migration of hydrogen, gamma hydrogen, followed by the cleavage of beta bond. So this gamma hydrogen is moving to the functional group. So this double bond, it is moving here, and this beta bond will be completely cleaved off. And this is called Macroparty rearrangement. As a result of that, you are going to get CH2 becomes, because this hydrogen is moving, it is becoming CH3, CH, double bond, CH2. This is what is seen, and this is called as MR ion. As I said, MR ion will have an even M by Z. Look at this. We can call it as M by Z or M by E. Both are, M by Z is also mass to charge ratio. M by E is also mass to charge ratio. You should know both. That's why I have given M by E here. And this M by E is appearing at even value of 42. Along with MR ion, yes, always MR ion should be represented by radical cation. Along with that, you are going to have a neutral molecule, that is alkene in this case. The next example that we can take is alkyne. So this is the functional group, and you should have 3 carbon atoms attached to the functional group, 1, 2, 3. So this is alpha, beta, gamma. Macroparty rearrangement says migration of gamma hydrogen followed by the cleavage of beta bond. So this is alkyne having M by Z of 68, and this is the molecular ion. That's why we have written radical cation. So here gamma hydrogen is moving. As a result of that, one of the bonds is moving here, and beta bond is getting ruptured. This is Macroparty rearrangement. As a result of that, CH becomes CH2, double bond C, double bond CH2. This is what is seen here, and this is Macroparty rearranged ion whose M by Z should appear at a even value, and that is 40. Along with that, we are going to get an alkene. See here, CH2, double bond CH2, that is alkene is obtained as a neutral molecule. The next example is substituted aromatic compound, that is substituted benzene. In this case, this is N-propyl benzene. So this is benzene is the functional group. To that attach 3 carbon atoms, 1, 2, and 3. So this is becoming the gamma hydrogen because alpha, beta, gamma. Now this gamma hydrogen should move here. This double bond is moving here. Beta bond will be cleaved off. So N-propyl bromine has got the molecular mass of 120. That is the molecular ion. After Macroparty rearrangement, what happens here? This double bond is moving here, and this becomes CH2, and this is CH2 double bond CH2 alkene neutral molecule is removed, and in this place 1 hydrogen is moving. So already 1 hydrogen is there. 1 more hydrogen is moving, so it becomes HH. So this is what you are going to get. Now this is not benzene ring. So this is a 6-member ring. Here there is 1 double bond, and here 1 more hydrogen is added. Its M by Z should appear at even value, that is 92. We will go for the next case. This is carbonyl compound. If Y is H, it becomes aldehyde. If Y is R, it becomes ketone. So in general, we have shown here. So carbonyl is the functional group. To that attached to be 3 carbon atoms, 1, 2, and 3. Alpha, beta, gamma. Gamma, there is hydrogen, no doubt. So movement of gamma hydrogen followed by the cleavage of beta bond. So this is the beta bond. Hydrogen is moving here. As a result of that, O becomes OH. This C double bond O is coming here. So it becomes C single bond O and C double bond C. And here it is CH2. See here, O has become OH, C double bond C, CHR dash. Along with that, you are going to get a alkene, and this is highly unstable. And as a result of that, so this is nothing but your enol. So the rearrangement will be taking place here. This bond is moving here. It becomes C double bond O, and oxygen will be retaining the plus. And we are going to get a rearranged product. And this is Macroparty rearranged ion. And this is the next example. This is a carboxyl function derivative. If Y is H, it becomes carboxylic acid. If Y is OMe, that is methoxy, it becomes ester. If Y becomes OET, then also it becomes ester. If Y is NH2, it becomes an amide. Now we will see if to this functional group attached are 3 carbon atoms, 1, 2, and 3. So this is alpha, beta, gamma. Macroparty rearrangement is migration of hydrogen atom followed by the cleavage of beta bond. So this hydrogen is easily moving to this oxygen. This becomes OH. This double bond is moving here. This becomes double bond CH2. So this should be O. Sorry, it has misappropriately written as C, but this is O. This is OH and double bond CH2. Its M by Z will be definitely should be even 60, 74, 82. In case of amine, if Y is NH2, then it becomes 59 in rare cases. Along with that, you are going to get a neutral molecule, that is alkene. This is about Macroparty rearrangement. But sometimes, if the molecule has got a functional group and either on either side of it, if it contains 3 carbon atoms, then you will see double Macroparty rearrangement. That is called double MR. So it involves conversion of intermediate enol to ketone followed by the hydrogen transfer to the enolic oxygen. So this is the functional group. This is the ketone. On either side of the functional group, that is ketone, you have got 3 carbons, 1, 2, 3. Here also you have got 3 carbons, 1, 2, and 3. Now we will do the first Macroparty rearrangement. What happens here? Here the first hydrogen will be gamma hydrogen will be moving, and this double bond is shifted here, and the beta bond is cleaved off. As a result of that, what you are going to get? This remains the same, CH3, CH2, CH2, and it becomes O becomes OH. Here OH is there, and this becomes double bond CH2, and this alkene is removed here. Now this becomes a functional group, and here the intermediate enol will be converting into a ketone, and the hydrogen transfer to the enolic oxygen will be taking place. As a result of that, here also there is another C3, C1, C2, C3. This is alpha, beta, gamma, and gamma hydrogen will be easily migrating. So as a result of that, second Macroparty rearrangement will also be taking place. So what happens here? The hydrogen will be moving here. This is here. The beta bond is cleaved off, resulting in the formation of an enol by removing one alkene neutral molecule. So this is the rare case. This double MR takes place only if the functional group on either side it contains minimum of 3 carbon atoms. Minimum there should be 3 carbon atoms. If there are 3 or more carbon atoms, then also Macroparty will be taking place. But minimum attached to the functional group there should be 3 carbon atoms. So this is all about Macroparty rearrangement, single Macroparty and double Macroparty rearrangements. In connection to that, you are going to solve exercise 3 and solve this by yourself. So this is CH3, CO, CH2 thrice, CH3, a substituted ketone. Now first thing you should do is the functional group should have minimum 3 carbon atoms. Yes, definitely there is 3 carbon atom. You can easily do the Macroparty rearrangement. Here in this case, this is a carboxylic acid. This is also having 3 carbon atoms. This is another ketone having 3 carbon atoms. In this case, we have to be very, very careful. All the compounds will not show Macroparty rearrangement. For example, this is the carbonyl group. On either side of that, there is an ethyl group. Ethyl has got only 2 carbon, but the prerequisite for Macroparty is it should have 3 carbon atoms. There are no 3 carbon atoms, so this compound fails to show Macroparty rearrangement. So also this, and here in this case also, in this case, this molecule will show this is a substituted aldehyde. This is 2-methyl butanol and this is 3-methyl butanol. Where the both are isomers, no doubt, but by using mass spectrometry, you can easily distinguish between 2 pairs of isomers easily, depending on the substitution pattern. To solve this by yourself, if at all you have got any problem, then you can come to me on the YouTube channel for the doubt clarification. This is about Macroparty rearrangement. Thank you very much.